So we're moving along here. Today we're going to be talking about taking derivatives for exponential functions. In the last two sections, you learned about exponential and logarithmic functions. Now we're going to talk about actually applying our calculus concept to these functions. So taking derivatives for exponential functions today is going to focus on just actually finding derivatives and then using the derivatives with all the techniques that we talked about in chapter 4. For instance, looking at intervals where the function's increasing or decreasing. Also talking about absolute extrema, doing an application problem, and I'm going to add an example at the end for implicit differentiation because it maybe has been a while since you've looked at that. So I'm going to add that today. So you'll have that to look forward to at the end. So our objectives are to differentiate e to the x in conjunction with all the previous differentiation rules and applications. That basically means we're going to do everything we've been doing already just now with exponential functions. So let's get started. First of all, the derivative of e to the x. Don't panic, the derivative of e to the x is e to the x. So that is at least sort of a welcome addition to what we're learning about here. So that as long as you just have e to the x, its derivative is e to the x. Now, let's say you have a situation where you have an exponential function with a base of e, and it's being taken to an exponent that's some function of x. In that case, the derivative is going to use the chain rule. So that's going to be e to the power f of x, and then you're going to chain on the derivative of the inside function. So just like we did when we used the chain rule 2 chapters ago, we're going to be using that now with exponential functions. So we're going to keep our original function the same, and then we're just going to multiply by the derivative of the inside function. Those are the 2 rules we're going to be using today. I know it seems so simple, right? What could possibly go wrong? It's not too bad. Find the derivative. Let's go through a couple of examples of how to find derivatives. Example 1. We'll say we have y equals x cubed plus 3e to the x plus 2 over e to the x minus e to the 4th power. All right, one thing I want you to note right away is that e to the 4th power is actually a constant term. Now, a lot of times, students think that because it contains a letter, that it must be some sort of variable expression. But remember, e is just a number, and it's being taken to a power that's also a number. So in this case, when we take its derivative, we're going to get 0 for that term. So I wanted to point that out right away. Another thing that we're going to do that we did in previous chapters is before we take the derivative, we're going to rewrite the function to simplify. There's not a lot we need to do, but we can't have this e to the x in the denominator if we want to take its derivative using these rules. Now, we could, if we wanted to, use the quotient rule here since the variable is in the denominator, but it's going to be easier to use this by use our rules with the chain rule if I just write this expression. So I'm going to rewrite it as x cubed plus 3 e to the x plus twice, and then e to the negative x. So when you bring that e to the x up into the numerator, remember the exponent becomes negative. Now we have this, we'll go ahead and take its derivative. So we'll say y prime is 3x squared plus, and now we're going to use that constant multiple rule. If I'm just multiplying this function of x by a constant multiple, I'm just going to keep the constant multiple and multiply that by the derivative. And the derivative of e to the x is e to the x. So the derivative of 3e to the x is 3e to the x. That does not change. As far as the next term, I'm going to take this derivative and we'll simplify it in the next step. But this will be twice using the constant multiple rule. But now I need to use the chain rule because I don't just have e to the x, I have e to the negative x. So the function in this case is negative x. That means I have to use the chain rule. I'm going to write this as 2e to the negative x, and I'm going to chain on the derivative of the inside function. The inside function is negative x, and the derivative with respect to x of negative x is -1. So that's what we're going to be chaining on here. So when we do this, we'll be multiplying by -1. And then the derivative, we said, of e to the fourth, because it's a constant, will be 0. Or -0, however you want to write that. So now we can just rewrite this by multiplying this -1 into this expression. So we'll say that we have y prime equals 3x squared plus 3e to the x minus 2e to the negative x. That is your derivative. Now, having seen this done with e to the negative x, that's a really common term we're going to be looking at, or this expression, e to the negative x. When you see that and you go to take its derivative, you can just automatically multiply it by a negative. You don't need to show all of this work. Let's do another one. We'll step it up a notch here. Number 2. This one is going to be f of x equals x e to the square root of x. Now, I'm hoping that as you're looking at these functions, it's kind of, you're scanning them and kind of thinking about the types of rules that you're going to need in order to find the derivative. Now, I'm hoping you're thinking right away like, ooh, this is going to need the product rule. And if you're thinking that, great, awesome, I'm really happy. If not, remember that we're going to need the product rule to take this derivative because we're taking one function of x and we're multiplying it by another function of x. So this one cannot be done without the product rule. Sometimes students forget to use that when they need to. What I am going to do, though, is just rewrite this because we are going to be taking the derivative here. You might find it more helpful to write square root of x as x to the 1/2 power. So we'll do that. Now, since you know already that we're going to be using the product rule, and if we let one portion or the one factor here be x and the other factor will be e to the x to the 1/2 power. When we're using our product rule, we're going to label these f and g. It might be helpful to you right now because this is a new concept to write these derivatives off to the side. Now, since I'm going to be labeling them f and g, I know this is so obnoxious, but I'm going to rewrite this f x that I started out with as an h, just so I don't have two different f's that I'm looking at in my expression. So just calling it an h so I don't have two different f's sitting there. Wonderful. So then we'll see that this one is f and then this other factor is going to be g. Great, I'm going to need to go ahead then and list their derivatives before I put them together with the product rule. So we're going to say that this needs the product rule. And then we'll go ahead and find the components that we need in order to do that. So we said that f of x was x. G of x is going to be e to the x to the 1/2 power. Well, some of these components are going to be very easy to find. The derivative of x is 1. But the derivative of g is going to need a little bit more work because g is an expression inside the exponent. So this one is actually going to need the chain rule. So we're going to be using the product rule and the chain rule here. So when I take the derivative of e to the x to the 1/2 power, I'm going to leave the expression the same at first. And then I'm going to multiply by the derivative of the inside function. So the inside function is x to the 1/2. And then that derivative is going to be 1/2 x to the -1/2. I'm going to multiply this here by 1/2 times x to the negative half. And you can simplify this now if you'd like, or you can just pop it into your product rule and then worry about it later. I will leave that up to you. I'm personally going to just simplify mine now. So I'm going to rewrite my G prime as, I'm going to leave e to the x to the half in the numerator. And I'm going to leave this 2 from the 1/2 in the denominator. And then x to the 1/2 I'll bring down into the denominator. Or as x to the negative half, I'm going to bring it down into the denominator as x to the positive. If you'd like to rewrite these with radicals, that's fine. You might find the algebra easier to work with using radicals. So if you would like to rewrite this as e to the square root of x divided by twice the square root of x, I personally find that's a lot easier to look at for me. So I'll leave that up to you. Okay. Now let's go ahead and put this together using the product rule. So we will do. Sorry, I'm just like checking. I did something really bizarre. I'm trying to figure out why. Okay. H prime. So we have here f prime g. So f prime is 1 times g, which is e to the. If you want to just write g as e to the square root of x, that's fine. And I'll just go ahead and label these as I'm going through. F prime g plus f, go ahead and label that, times g prime. So the g prime that we have is e to the square root of x divided by twice the square root of x. We'll simplify this. There's a lot that we actually need to do to simplify it. Oh, you know what? I did not label this. F prime g plus f g prime. I think you're pretty familiar with using your product rule now, so we should be good. All right. One thing that might be sticking out to you as something you want to do is factoring out e to the square root of x. I'll leave it up to you. I'm probably going to leave mine in for right now, but we might end up deciding to write this in 2 different ways. So the first term is going to be e to the square root of x. For the next term, I want to simplify between the x and the square root of x. Now, part of me is wishing I would have left this as x to the 1/2 power. But remember, I can bring this back up into the numerator, and that might make it easier for you to see what's going on. So the 2 in the denominator, we can rewrite as a half. And then you have x times x to the negative half. If I bring this up to the numerator, I'm going to switch the exponent to be negative again, just to simplify this. And then e to the square root of x. Now, when you're multiplying with the same base, you add the exponents. 1 minus a half is positive 1/2. So this will be e to the square root of x plus, and then x to the positive half, e to the square root of x. You can leave the 1/2 in front, or you can divide by 2, whatever you want to do there. This is fine. Personally, I feel like it's weird to mix rational exponents and radicals. So if it were me, I would probably leave it as e to the square root of x plus 1/2 square root of x e to the square root of x. Another thing that you could do is factor out the e to the square root of x. Don't forget, though, that when you do that, you still have a 1 as your first term. And then plus 1/2 times the square root of x. Sometimes students think that this looks better, and that's fine, as long as you do it correctly. Sometimes we mean well by simplifying things, and we end up making mistakes in our simplification, and then we get an answer that's not equivalent. So. All All right, that is how we use the product and chain rule together. So even though the derivative of e to the x on its own is pretty straightforward, we still have to use the derivative rules that we already know and love in order to find these derivatives. So sometimes they become, not more complicated, but as complicated as some of the derivatives we worked on in chapter 3. All right, I have one more example here that I think will help with these derivative rules. The example is h of x equals e to the 1 over x divided by x. So now this one needs the quotient rule. Technically, you could use the product rule by pulling that x up into the numerator. I don't know that it really makes a difference. Personally, I would probably just use quotient rule because there are variables in the numerator and the denominator, but that's up to you. I'm going to use quotient rule. All right, so to use the quotient rule, I'm going to go ahead and label these f and g. And then we'll go ahead and take their derivatives. And you'll notice that when you label f as the numerator, e to the 1 over x, your f prime is going to need the chain rule because the derivative of e to the 1 over x is e to a function of x. You're going to have to use the chain rule there. So if you would like to rewrite this as e to the x to the negative first, that's fine too. And then your g of x function is just x. So now we have f, we have g. Let's go ahead and take the derivative of f. Remember, when we're using the chain rule, we're first just rewriting the function as is. So it's kind of up to you the way you want to rewrite this. I might just leave my exactly as it is without the rewrite, but I am going to use the rewrite to find the derivative of the inside function. So in this case, we could say that our inside function is x to the negative first. And when we change the derivative of the inside, we need to go ahead and get this derivative. So we would say that the derivative with respect to x of x to the negative first is -1 times x to the negative second, which is -1 over x squared. So this is what we're going to chain on here for f prime. So it's just the original function multiplied by the derivative of the inside function. The inside function is to the negative first, which is 1 over x. When we take its derivative, we get -1 over x squared. So I'm going to multiply this by -1 over x squared. And then if you'd like, you can rewrite that right now. I'm torn, but I think I might just rewrite it right now. So we'll write this as -e to the 1 over x divided by x squared. And then g prime is 1. Trying to make that look less crowded, and I was going to put a box around it, but I'm like, I don't know that I'm going to make that look any better. I kind of crammed a lot of information into that little blank there. Sorry. But now we have all the components we need, and we can put them together with the quotient rule. So let's do that. H prime. So this is going to be f prime g minus f g prime over g squared. So f prime is that derivative we just found. So f prime is going to be -e to the 1 over x divided by x squared. So that's f prime, and then g is x minus f, I'm going to leave it as is, times g prime, all divided by g squared. And I'm going to label this too so that it's clear where everything's coming from. So this is f prime g minus f g prime all divided by g squared. And then we'll simplify. We actually are going to have a little bit more simplification to do here. One of the first things I would do is just multiply here between 1 over x squared and x to cancel out a factor of x. So I'm going to go ahead and do that first in the first term in the numerator. So we'll say that this is negative e to the 1 over x divided by, and then just x to the first power, because you're canceling out that common factor of x here. And then we'll have minus e to the 1 over x divided by x squared. Now, don't leave it like this, because this answer is considered to be a complex fraction. In order to simplify a complex fraction, you need to go through and multiply every term by the least common denominator. So that's what I'm going to do next. I'm going to multiply each term by the LCD. Multiply each term by the LCD to simplify. And the LCD in this case is x, because looking at each individual fraction that you see, and you're looking for the least common denominator of the denominators, and this is the only like fraction within a fraction that you have. So your LCD in this case is going to be x. The goal here is to get rid of this common factor, or get rid of this compound fraction, or this complex fraction, I should say. That's the goal. So the idea here is, as long as I multiply by the LCD, well, now I can take this x and cancel it with that x. And now I don't have a fraction within a fraction anymore. So now I just have negative e to the 1 over x minus, and then now I have an x times e to the 1 over x. And then we'll divide that by x cubed. Whatever you do, don't try to cancel these x's. You cannot do that. Remember, you must be able to factor it out before you can cancel it. And this term doesn't have an x to factor out. So this is fine. This answer is completely fine, totally acceptable. If you weren't sure how else to simplify it, just leave it like this. But this is another instance where maybe I would say, if you felt comfortable with your factoring out a negative e to the 1 over x would be a really nice thing to do here, because that would leave you with just a factor of 1 plus x in the numerator. I know, I feel like it looks a little bit more concise that way. But it's up to you. Make sure that you always check and make sure that when you multiply it back in, you get exactly what you started with. Either one of those is fine. So those are the exponential derivatives. What we'll do now is we'll do some applications with these derivatives so that you can get a little bit of work with them. One thing I really love about this chapter is that you're reviewing all the previous concepts while you learn new derivatives. So you don't get a chance to be like, wait, I forgot everything we did in chapter 4, because we're going to be doing it all over again throughout this chapter. You're welcome. Find the equation of the tangent line to f of x equals e to the negative x. And we're going to look at this at 1 over e. All right, so if I'm finding the equation of the tangent line, what I need is the slope. In order to get the slope, I need to find the derivative and evaluate it at the x coordinate, the point that I've been given. So go ahead and find the derivative first. F prime of x, remember, is e to the negative x. Keep your function exactly as it is and multiply by the derivative of the inside function. The inside function is negative x. The derivative of negative x is negative 1. So this is negative e to the negative x. Now that gives me a slope for any given general point that I want to find. I'm talking about the point at 1 over e. So I'm going to evaluate the derivative right now at 1, which is the x coordinate of this point. So I'm going to evaluate it at 1. That leaves me with e to the negative first. I forgot the negative in front of it, but wait, it's the negative. Oh, never mind. The negative's already there. X is positive. So it's negative e to the negative 1. Now, you could technically leave this in that way. I like to write my exponential expressions so that they have positive exponents. They usually will simplify a little bit more easily, but I also just feel like algebraically they're a little bit easier to work with. So I prefer this, but this is not wrong to leave it as negative e to the negative first. I think this looks better though. So this is my slope. I just think it's going to be easier for you to work with it algebraically. So the two things I need to write an equation for a line are a slope and a point. Right now I have a slope, I have a point. I'm going to put those together with point slope form to write the equation of this line. So we have y minus y sub 1 is 1 over e. That's another reason it's nice to have it in this form, so it matches the form that you're given. All right, equals m times x minus x sub 1. And then we'll simplify. So we have y minus 1 over e is negative 1 over e x plus 1 over e. We distribute into the parentheses. And then we'll go ahead and solve for y. So now I have negative 1 over e x plus 1 over e. And then I'm going to add the 1 over e from the left-hand side to both sides. And this is going to be a lot easier for you to work with than if you would have left this with a negative exponent. So now I can simplify this by saying that y is negative 1 over e x, and then 1 over e plus 1 over e, well, they're fractions and they have the same denominator. When you're adding two fractions with the same denominator, you just need to add their numerators. 1 plus 1 is 2, so 1 over e plus 1 over e is 2 over e. And that is the equation for the tangent line at the point 1 over e. We haven't looked at these in a while, so I'm gonna do that now because I would feel like we were missing something if I did not do that. So let's do that now. I don't want to feel like we're missing something. I don't want to cheat you out of this experience. All right, the equation is e to the negative x. So to enter my e, remember I'm going second and then the log button. That's going to pull up our e. There we go. And then that's being taken to the negative power. So I've got this situation now. I don't know. We'll zoom standard because I have no idea what zoom I'm in right now. The point I'm looking at is 1 over e. So it's right here. So let's go ahead and write this equation in and make sure that it's tangent at that point. So this is going to be negative 1 over e. Now, when you enter e, it always wants an exponent. So if it's just e, just enter e to the first. So this is negative 1 over e x plus 2 over, and then again, 2 over e is just 2 over e to the first. I know this looks a little bit weird, but if you'd like, you can put a multiplication symbol before the x, but you shouldn't need one. Graph it. There it is. It is indeed tangent when x is 1. Y is, I don't know, just like a little bit around a half, a little bit less than that. So, yeah, I guess we could look at the value. If x is 1, y should be about 0.3679. So, yeah, I'll go more than a third. Definitely less than a half for your y value here, but it does not matter. You can see that the line is tangent at that point in the curve. Yay! You know I love that. I love that. Okay, we need to be able to see the results, otherwise it means nothing to us. Moving on. Find where fx equals e to the negative 1/3 x cubed is increasing and decreasing, as well as the local extrema. Okay. So in order to do that, this is what we were doing in chapter 4 in the first section. We were using the first derivative test to find extrema and to look for intervals where the function was increasing or decreasing. In order to use that test, we need the first derivative. So let's find the first derivative, and we'll get the rest of this information based off of that. All right, so f prime, this is not e to the x, it's e to a function of x, but I don't need the product rule because I'm not multiplying it by anything. I just have a function on the inside in the exponent. So I'm going to leave this function the same, and I'm going to chain on the derivative of the inside function. Now remember, your inside function, well, in this case, it's just negative 1/3 x cubed. So when we take its derivative, this is a pretty straightforward derivative for us to do. We're just taking the derivative of negative 1/3 x cubed. And when you do that, you're going to use that power rule for exponents and bring this 3 out front, and you'll get negative x squared. 3 times negative 1/3 is just negative 1, and you decrease the exponent by 1. So when we multiply by the derivative of the inside function, we're multiplying by negative x squared. Now, because we're going to be using the first derivative test and we need to find critical numbers, in the last chapter, we're often setting up our first derivatives as fractions so that we could look at the numerator and denominator separately. I'm going to do the same thing here. So I'm going to write this as negative x squared divided by e to the positive 1/3 x cubed in the denominator. And that is going to be your first derivative. In order to look for local extrema and cutoff values where it might be increasing or decreasing, we need to find critical numbers. So I'm going to say find critical numbers. In order to do that, I'm going to be looking for places where, first off, the first derivative is equal to 0. Now that's going to happen when the numerator equals 0. So that means negative x squared equals 0. And that's only going to happen when x equals 0. That's the tricky part. What I've found is that students often have a really hard time looking for critical numbers where the base e is involved. So if I was going to look for critical numbers where f prime does not exist, I would want to look for where the denominator was equal to 0. Well, if I did that, I'd be saying, all right, well, I'm looking for e to the 1/3 x cubed to be equal to 0. And this is where students sometimes get stuck. They're like, I don't know. I don't know how to proceed. Well, first off, I'm going to tell you one thing. Think about this logically with what you know about bases and exponents. You're saying e, which is some real number, 2.7 something, to a power has to be equal to 0. Can you take a real number to a power and get it to be equal to 0? I mean, like if this was e to the 0, you'd get 1. You know if 0 is the exponent, it will equal 1. But what does the exponent have to be in order for this to be 0? Can you find one? I mean, if base is a real number, think about it. Like, there's not going to be an x where this could possibly happen. And let's say, I'm going to go ahead and tell you, none. But if you weren't sure, you might decide like, well, maybe I want to isolate the variable. That's fine. You could take the natural log on both sides. That's what we usually do to like undo e. And then if you did that, you would get e to the 1/3 x cubed. Oh, sorry. This is, this is supposed to be in the exponent, but I wrote it and it does not look like it's in the exponent. And I want to make sure it's not misleading. Okay. 1/3 x cubed is ln 0, but ln 0 doesn't exist. Remember, you can't take the natural log of 0. When you take the natural log of a number, that number has to be positive, not 0, not greater than or equal to 0. It has to be greater than 0. The natural log of 0 does not exist. So you don't have any critical numbers that could possibly be making this denominator 0. So the only critical number you have is x equals 0 right here. All right, but now you can do a sign analysis on that. If you would have had like x times e to the 1/3 x cubed, that would have been a different story. Then you'd be like, okay, well, if x equals 0, this expression could be 0, but you didn't have that. And a lot of times you won't have that. So if it's just some exponential expression, your base of e equals 0, you're not going to have any critical numbers come out. Okay, now, if you're thinking about your sign analysis and you're like, hey, didn't she just say that the natural log was only valid for positive numbers? Does that mean I need to do a sign analysis on negative numbers? Yes, because remember that your sign analysis is going to be based off your original function. And the original function's domain is all real numbers. Your exponential expression can be evaluated for any exponent. So e can be taken to any number and yield any number. So e to the negative 1/3 x cubed has a domain of all numbers. So that means when you do your sign analysis, this is officially heading all the way down to negative infinity and all the way up to positive infinity. We're going to chop that off at 0 because that's our critical number. We expect something is changing, something's happening there. And you're going to test a value. I'm going to test -1 and +1 because why not? Oh, like butterfingers over here. I'm going to test -1 and +1. So I'm going to say f prime of -1 and f prime of +1. And we're going to see if the value we obtain is positive or negative. I'm going to put my first derivative into my calculator. This one I don't need anymore. So the first derivative is -x² divided by, this should not need parentheses, but you can always include them if it makes you uncomfortable to not have them. E to the 1/3 times x cubed. You don't even need the times sign, but sometimes it makes me uncomfortable to not have it because sometimes I need it when I'm doing other programs and it just, I just want to use it here too. Anyway, so now we'll go to our table, -1 and +1. +1 I already had entered here, but -1 is negative 1.396. And for +1, I get negative 0.717. So in both cases, I get decreasing because in both cases, I get a negative value. So if I know the function is going to be decreasing on both intervals, I can write that down. I can say it's decreasing. And be really careful with how you write this. I know I've said this before, but I saw some people do this incorrectly on the exam. When you are decreasing, make sure that if you have a critical number somewhere splitting up your interval, even if your increasing, decreasing doesn't change, you still have to stop the interval and restart it. What this means is at 0, the function's not actually decreasing. It just stopped decreasing for a moment. So we're going up to 0. And then picking it back up at 0 and going up to infinity. It's not increasing anywhere, but we can say that we have no extrema. And we have no extrema because the sign of the derivative is not going to change. It's always going to be negative. And I mean, it just means our graph decreased and then it stopped decreasing and then it decreased again. If you want to see what that looks like, we'll pop it into our calculators. I can just get rid of this, right? Yes. E to the negative, this is our function. I'm just going to graph function so that we can verify that this looks like what's really happening in the function. So this was our function, e to the negative 1/3 x cubed. I put this into my graphing calculator. The only interesting thing is happening at 0. We should be able to see that in our current Zoom, Zoom 6. We'll graph the function, see what happens. All right, so it's decreasing all the time, except for at 0. So it's decreasing, decreasing, decreasing. It seems to like go constant for a split second, and then it decreases again. Now, if you're like, oh, that looks more complicated than what our data is showing, well, it has to do with the concavity changes that are occurring. So maybe we should look at concavity next. We were going to do that anyway, but that's what's happening with the function as far as increasing, decreasing is concerned. Okay, now let's look at the same function and look where it's concave up or concave down. Same function. So we already have the first derivative. F of x is e to the negative 1/3 x cubed. We're going to look at where this function is concave up and down. Now, we already found the first derivative in example 2. We found that it was negative x squared divided by e to the 1/3 x cubed. Now we'll take the second derivative. F double prime of x. All right, so f prime g minus f g prime. So g prime we already, let's see, no wait, actually we did not already find g prime because this was to the negative exponent, but that's okay, we'll do that right now. So we have f prime g minus f g prime. I'll write this off to the side here. It's going to be basically the same as what we found up here, just the sign is going to be different. So the inside is going to be 1/3 x cubed. So we're going to take ddx of 1/3 x cubed, and we're just going to get x squared. So when we take g prime, we're going to take our exponential expression in the denominator, e to the 1/3 x cubed, and multiply by the derivative of the inside function, which is x squared. And then divide by g squared. So this will be e to the 1/3 x cubed squared. And then we'll simplify. Now, anytime you're taking a second derivative, you usually have something you can cancel. And in this case, we absolutely do. We have 3 instances of e to the 1/3 x cubed. You can take out one of them in each term. So in the denominator, we're just going to take away 1. We still have 1 left over. But now we can say that f double prime of x is negative 2x, and then minus a negative is plus x to the 4th power divided by e to the 1/3 x cubed. And we'll find some possible inflection points based off of that. Now, this is a really similar derivative that we found to the one we found in part 1. Which was, remember we outlined it here. We took the derivative or we took the denominator, set it equal to 0, and we were like, okay, well, that can't be. We're going to do the same thing here. But basically, you can just state this, f double prime of x does not exist. You're not going to have any values there. So if you just want to note that right now, you won't even have to look at it again. And then as far as your f double prime being equal to 0 for possible inflection points, well, that's going to happen when negative 2x plus x to the 4th equals 0. Now, to solve this, remember what not to do. Do not, tell you what not to do. Don't do this. Where you're like, okay, I'm going to add 2x to both sides. I'm going to cancel out a factor of x. And then I'm going to say x equals the cube root of 2. That's close. But remember that when you do this, you've canceled out a factor of x on both sides of the equation, and you lost a solution there. So even though, yes, this is going to be one of our solutions, we can't do it that way, or we're going to lose the very valuable solution where x equals 0. So I'm going to go ahead and do it the way that I would like to see you do this. So I'm going to go ahead and factor out the common factor of x, and that leaves you with -2 plus x cubed equals 0. So what that means is -x equals 0 and -2 plus x cubed equals 0. So x is 0 and x is, for the same reason we did this over here, you could say x cubed is 2 and x is the cubed root of 2. Remember to undo the cube on x, you take a cube root on both sides. If you're wondering, like, do we have to take a plus or minus like we do when we square root both sides? Remember with a cube root can be a negative value for a negative number. You don't do a plus or minus when you apply the cube root. You only do that when you are applying even roots. So 0 and the cube root of 2 are possible points of inflection. Remember that if the concavity actually changes at those values, then we'll officially call them inflection points. But for now, all we can do is stack them in a sign analysis to see if that's occurring. So let's go ahead and do the sign analysis. I, again, have all real numbers for my domain. So I'm going to go ahead and check 0 and the cube root of 2. If you're checking the cube root of 2 and 0, you especially need to figure out what the value for the cube root of 2 is. The cube root of 2 is 2 to the 1/3, which is about 1.26-ish. So you have some sort of clue where your test points are going to lie. I'm going to test -1. And +1 will work because it's between 0 and about 1.26. And then the next one I'll test is 2. So we'll do all 3 of those. I'm just going to put these in my calculator. That will be, I think, the easiest thing to do. Oh, I should have kept that in there. But that's okay. F double prime is -2x. Oh, you know what, though? Let's put parentheses around our numerator. Plus x to the 4th, because our numerator is more than one term. And then we'll divide that by our second derivative. We'll divide it by e to the 1/3 x cubed. Make sure that x cubed stays in the exponent. And then we'll go to our table and we'll look at -1, which I already have in there, 1, which I already have in there, and 2, which I already have in there. It's positive, negative, positive. So positive, negative, positive. So we can go ahead and make our conclusions about concavity. If it's positive, we're concave up. Negative means concave down. Positive means concave up. Now, remember, I'm going to ask you to list your inflection points as ordered pairs. So I'm going to write mine exact in just a minute. I'm going to go ahead and make my conclusion first. So concave up from -infinity to 0. And then from the cubed root of 2 to positive infinity. And then concave down on 0 up to the cubed root of 2. Okay, so there's that. Okay, now I'm looking at the directions and it's defined where it's concave up and down, but I really want us to list these as ordered paired inflection points, even though you weren't asked to do that. I know I'm always making you do all this extra stuff, but it's really good for you. So let's go ahead and figure out what those ordered pairs would have to be. F of 0, because I'm looking for where this inflection point would lie. The first one happens at 0. I'm going to look at my actual function f, which is way back here. It's e to the negative 1/3 x cubed. And that's just e to the 0. E to the 0 is 1. So I know I have an inflection point at 0, 1. I'll write that down in a minute. Well, actually, I might as well just list this here. Right now, I got one more that I'm going to list, though. Point of inflection at 0, 1, or 0, f of 0. And then the other one is going to be f of the cube root of 2. Don't panic, because we have a cube here. F of the cubed root of 2 is e to the negative 1/3 times the cube root of 2 cubed. Now the cubed root of 2 cubed is 2. So this will just be e to the negative 1/3 times 2. So the cube undoes the cube root. So that means that f of the cube root of 2 is just e to the negative 2/3. I know that you were panicking and you were like, nope, nope, this looks bad. I want to do it. You must. It will simplify nicely most of the time for you here. That's our other inflection point. So you can even write this. Ooh, I'm going to get super fancy. You can write this as 1 over e to the positive 2/3. Or you can leave it negative. It doesn't matter. But the point is it's exact, and that's what we like. Exact values. So we have the cube root of 2, and let's just say it's e to the negative 2/3. Excellent. I'm not done yet, though. You know, there's a lot to do here. There's a lot to unpack. Let us see. Find the absolute extrema. Remember, absolute extrema, we're talking about the absolute biggest and the absolute smallest values that are going to occur on an interval. Find the absolute extrema of f of x equals e to the negative quantity x squared plus 1 on the closed interval from -1 to 1. So remember, what we're going to do is we're going to find the first derivative. We're going to find critical numbers. We're only going to look at critical numbers that are inside this closed interval. And then we're going to test the y values at the endpoint and test the y value at the critical number and figure out which one is the largest and which one's the smallest. So let's go ahead and get started by finding the first derivative, f prime of x. So remember, to do this, we're just going to keep our expression exactly the same. And if you're wondering, like, why do we have this negative factored out, you can always put it back in if it's bothering you. I don't know. That's up to you. Maybe I'll just, I don't know. I'll go ahead and multiply mine in. Why not? Negative x squared minus 1. I think that makes me feel happier about it. Okay, chain on the derivative of the inside function. The inside function is negative x squared minus 1. Its derivative is negative 2x. Okay. So now we can rewrite this as negative 2x divided by, and now we can put this back into the denominator. Remember how we rewrote it? I'll give you the equivalent here. Because it's a negative exponent, now we can bring it into the denominator and make it positive. That's just a little bit of a fancy move we're going to do here. So no, it's no longer negative now. It's positive. I just wrote it like this so that we could easily take the derivative without having to worry about the parentheses. All right, but we want to have your derivative written as a fraction so we can most easily find our critical numbers. Let's go ahead and figure out what our critical numbers might be. I'm going to take f prime of x and set it equal to 0. And that means the numerator equals 0. And that means that x equals 0 is a critical number. Now, remember, with these absolute extrema on a closed interval problems, you need to verify that the critical number is actually in the interval. So we would say that, yes, it's inside this interval. Check. This is like in the set of these numbers. So 0 is inside the interval from -1 to 1. So we're good there. Then we're going to look for places where the first derivative does not exist, which means e to the x squared plus 1 equals 0. Well, I went into a whole thing about this on the previous page. The base is e. It's being taken to an exponent. You're never going to get to equal 0. If you took the natural log of both sides, you'd get x squared plus 1 is the natural log of 0. The natural log of 0 does not exist. So this could be none. So you only have one critical number. That's good. So to find the absolute extrema, you're not doing a sign analysis. You're going to be looking at the function values at the endpoints and the critical number, and then figuring out which one's largest and which one's smallest. So let's go ahead and do that. All right, in my calculator, I'm going to enter my function e to the, and for simplicity, I'm going to write negative x squared minus 1. Whoops, got out of my exponent for a second. You know why this is confusing? It's I have an exponent inside an exponent. Well, that's not a minus, it's a negative. Okay. Negative x squared minus 1, or you can write it as negative x squared plus 1. I'll leave that up to you. You do you. Okay. And then I'm going to go to my table. I have -1, I have +1, I have 0 as values that are all sitting here already. -1 is about 0.1353. 0 is 0.3679. And 1 is 0.1353. So I have the same value at these endpoints here. So I'm actually going to have two values for the minimum. And then the maximum is going to be at 0. So, sorry, the notation's really confusing. I don't know how I ended up coming up with that. This is not good enough. You have to give me exact answers. List your answers exactly. 0.1353 is not exact. That's a truncated decimal. Let's go ahead and get some actual values here for these functions. This is really good practice for you anyway. So let's go ahead and evaluate. The reason it's nice to put these in our calculators is because in order to compare the numbers, we need to have decimal approximations. But if we're listing exact values, we actually have to go through and evaluate the function by hand. All right, so f of -1 is e to the -1 squared minus 1. So I'm using this definition just because I feel like it's easier to evaluate. So the -1 squared minus 1. I know it looks really like confusing. -1 squared is +1. This is +1 times -1. So you have -1 minus 1 is e to the -2nd. Now, you're going to see the same thing happening for f of 1 because we already saw in the calculator that they have the same value, but I'm going to switch my order here. Notice the reason why that happens is because -1 squared and 1 squared both give you the same value. So you're still going to end up with e to the -2nd. So we have that. As far as f of 0 is concerned, you have e to the -0 squared minus 1 is e to the -1st. So we can go ahead now and list our conclusions, and we can say that we have an absolute maximum And that occurs at x equals 0. The maximum value is e to the negative first. The absolute maximum, let's say, is e to the negative first, which is 1 over e. Maybe I should say equals 1 over e. Same thing. And this occurs at x equals 0. And then the absolute minimum is e to the negative second, which is 1 over e squared. And this occurs at x equals negative 1 and x equals positive 1. So the value of the min-max is the function value, and then it occurs at the x value. All right, I got 2 more questions for you. I got this one, and then I want to go over an implicit differentiation problem because we need to see that. The number of polio cases in thousands is n of t equals 5.3 e to the 0.095 t squared minus 0.85 t. That's all in the exponent. So it's 5.3 times e to the 0.095 t squared minus 0.85 t, where t is years after 1959. Find the number of polio cases in 1960. Okay, so find the number of polio cases in 1960 and how fast the number was decreasing in 1960 and how fast the number of cases was decreasing in 1960. The change in the number of cases is n prime. Okay, we need to be able to read these questions and see what they're asking. So if it's just find the number, cool, evaluate the function. If it's find how fast it was decreasing, we need to take the derivative. So we also need to be able to evaluate the function at a specific value of t, so it's important to be able to determine that value. This function is discussing t years after 1959, and we're being asked about 1960. So t equals 1. 1960 is 1 year after 1959. So the first part of this is find the number of polio cases in 1960. That's n of 1. So this we're going to put into our calculators, but it's going to be 5.3 times e to the 0.095 times 1 squared minus 0.85 times 1. We'll pop this into our calculators and get a value. So let's see, 5.3 times e to the 0.095 times, you don't really need 1 squared, but that's fine, minus 0.85 times 1. You should get 2.491-ish. What did I get? Let's see, 2.4911 as n of 1. Now, if you're thinking like, wait a second, find the number of polio cases in 1960. The number of polio cases is 2.4911. That probably doesn't make sense because you'd be expecting more. Well, remember that you were given information about polio cases in thousands. So this is 1,000 cases So this would be in thousands. So 2.49 thousand is like 2,000 something. So you can go ahead and move your decimal point over 3 places. Or, you know, honestly, you can just round this off at this point. So if it's 2.491 thousand, then it's 2491 cases. You'll be moving that decimal to the right 3 places, or just take this number that you have in your calculator and multiply it by 1,000. Oops, not add, multiply. And you get 2491.056. I would give you instructions, of course, for rounding, but this would be the way that you would answer this. So you wouldn't say 2.4911 thousand cases. Answer it with like actual number that's meaningful. In 1960. Okay, and then the other thing we're going to do here is find how fast the number of cases was decreasing in 1960. So in order to do that, we need to find n prime. And in order to do that, what we're going to do is take the derivative of this expression, which means we're going to keep everything exactly the same and multiply by the derivative of the inside function. So 5.3 times e to the 0.095 t squared minus 0.85 t, and then that whole thing is going to get multiplied by the derivative of the inside function. So 0.095 times 2 is 0.19. So the derivative of the inside function here is going to be 0.19 t minus 0.85. I'm trying to get better about writing my leading decimals here, but that is the derivative of the inside function. Now, you don't need to go through and simplify this at all. Just evaluate it. There's really not a lot you can do to make this look much better. But we're going to take now n prime 1. Now, the thing is, you already have some of this information in your calculator. So all you really need to do at this point is take the information you already entered, which is 5.3 times e to the blah, blah, blah. It was this number. Fine. That was what you had. And then you're going to multiply that by, in parentheses, 0.19 times 1 minus 0.85. And you get negative 1.644. Thousand cases per year. Remember that when you write a unit and you're talking about a rate of change, we need to actually put that rate of change into the unit. So it's not enough to say negative 1.644 thousand cases, but we need to say 1,000 cases per unit time because it's a rate of change. And again, just like we did in the first part of this problem, we don't want to write this as some 1.644 thousand. We just want to write this now as negative. I'm going to multiply it by 1,000. Or you know what? Actually, I'm not even going to put the negative here. Well, because you were asked about how fast the cases were decreasing. So let's make this better. So we'll see that the cases were decreasing by, and since we know that they're decreasing, we can lop off the negative because we've already said they're decreasing. So the cases were decreasing by 1,644 per year in 1960. And if you know anything about polio, that should make sense because there was a vaccine that came out and people weren't getting polio as much. So you'd expect the numbers would be decreasing. But this is, it does not say if it's worldwide or in a certain region. Is what it is. Okay, I have one more problem for you. Don't go anywhere. You can flip this page over because I want to go through an implicit differentiation problem with exponential functions. Maybe I'll flip my page over too. I need to use an extra paper. I'm going to go through one of these because I think you will see them on your homework, and I want to make sure that we are prepared when we see them. So let's do that now. Oh, she can't decide what color to use. This one. They say blue is a calming color, and I feel like at the end of the lesson we need to be calm. We'll call this example 6. Differentiate implicitly. E to the xy equals x plus y plus e to the x plus y power. Okay, maybe it's been a while since we took derivatives implicitly. Remember that we're going to differentiate x the way that we always would. We're going to differentiate y by tagging on or chaining on that dy dx. And we might have to do a little bit of work with distributing, but that's no big deal. Now, one of the things to note is that when we have x, y in the exponent, we're going to have to use the product rule. I'm going to remind you of the derivative of x, y. Recall d dx of xy was f prime g plus f g prime. We did this back in the section when we learned to take derivatives implicitly. I'm trying to remember exactly what section it was. I want to say it was 3.6. But we did this in 3.6. So we're going to have to multiply by the derivative of the inside function here. The derivative of the inside function with respect to x is 1y plus x dy dx using the product rule. Okay, so let's go ahead and take this derivative then. On the left-hand side, I'm going to keep my function the same. I'm going to multiply by the derivative of the inside function, which is y plus x dy dx, f prime g plus f g prime, equals. Now, on the right-hand side, the derivative of x is 1. The derivative of y is 1 dy dx. You always chain on dy dx when we're differentiating y with respect to x. And then for e to the x plus y, I'm again going to leave it as is, and I'm going to chain on the derivative of the inside function. So the derivative of the inside function is 1 plus dy dx. Move this out of the way a little bit. Okay, so taking the derivative here is no small feat. If you can get this far, that's most of the points in these problems. All right, so keeping the function the same, chaining on the derivative of the inside function. Note that these two look really similar, but they're very different. This one needed the product rule. This one did not. So this one, we're just leaving the function the same. And then the derivative of the inside function is just the derivative of x plus y, which is 1 plus dy dx. Now remember, the whole idea here is we're trying to solve for dy dx. So I need to get all the dy dx's on one side and all the non-dy dx's on the other. To do that, we're going to have to just distribute into the parentheses so that I can get these terms split up. So I'm going to distribute here, and I'm going to distribute here. So let's write what's next. So we have y, e to the xy, plus x, e to the xy, dy dx, and all of that's happening on the left-hand side. On the right-hand side, we have 1 plus dy dx, plus, and then I'll distribute. So we have e to the x plus y times 1, and then e to the x plus y times dy dx. Now that you have all the terms split up, you can take the dy dx terms and put them to one side. Oh, I knew that was something. It was unavoidable. Okay, and then move all the non-dydx terms on the other side. Now you have two of them over here. So if you're like, I just want to keep them all over here, I guess that makes sense. But I just like to have my dy dx terms on the left. It's just a thing. So I'm going to do that. So I'm going to keep this one here, x e to the xy dy dx on the left. Excuse me, I'm having issues over here. I'm going to move these two to the left-hand side. When I change the side, change the sign. So I'm going to have minus dy dx and then minus e to the x plus y dy dx. Everything else is going to either stay on the other side or move if it doesn't have a dy dx on it. So I already have a 1 on the right. I'll keep it there. I have an e to the x plus y on the right. I'll keep it there. And then the only other term I haven't touched is the first one on the left-hand side. I'm going to move it to the right, change the side, change the sign. There it is. I'm going to double check and make sure all my signs are correct. So this one stayed the same. These two went negative. Yep. These two stayed the same. This one went negative. Awesome. Once you have all the dy dx's on one side, factor them out. And that leaves you with x e to the xy minus 1 minus e to the x plus y. I know it's a lot of little things you got to watch out for here. Rewrite the right-hand side. And then the last thing you need to do is just isolate dy dx using division. So divide both sides by this factor on the left-hand side. So I'm going to say dy dx now is equal to, the right-hand side is going to be the numerator. I'm not going to change anything there. And the left-hand side factor is what I'm dividing out on both sides. And that one's going to stay. Now, remember that maybe over here you decided to bring all your dy dx's to the right and all your nons to the left. That's fine. If you did that, all of your signs will be exactly opposite. And that's okay. If your signs are exactly the opposite, that means that it's the same answer. You just multiplied by -1 over -1 essentially, and nothing actually changed in your expression. That happens sometimes with these, but this is the answer. And it's done. So bonus. Anyway, have fun working with these. If you have questions, let me know. And yeah, that's it. Enjoy the rest of your day.